Dear friends, my name is M.L.M.Prasad. I am going to teach formal language and automata theory. I am stick to J2H syllabus only. And actually the subject is very much useful in the concept of gate, and even if you go for any university to do MS in abroad, either in US or UK, in any other country. So this is one of the important subject in our MS degree also. So the subject is very much useful, in particularly for gate examination. So now there are many applications related to automata. So even in one of the examples, we can say compiler design and the lexical analysis phase, we use the concept of automata theory concepts. And even while checking, if you search in Google for if you are giving a sentence, then for checking phrases and keywords, even for those concepts also we need to use the concept of automata, like NFR, finite automata concept we need to use. Even in exchange of communication exchange, in the protocols also use the concept of automata theory. So there are many more applications related to automata. These are the, I given just some of the applications only. There are many more applications are there. Okay. So now the first concept related to formal language and automata theory is the central concepts of automata theory. The central concepts of automata theory. In that, the first definition we need to learn is symbol. What is meant by a symbol? Symbol is a basic building block of an alphabet. Symbol is a basic building block of an automata theory. Symbol is a basic building block. It may be, if I give an example like for symbol, it may be any alphabet AB or any symbol 0, 1 and so on. You can give many more. Symbol is a basic building block of an automata. It is any symbol, it may be any alphabet or any numerical like 0 or 1, 2 and so on. And then the next definition is alphabet. So this is my first definition, symbol. Then the second definition is alphabet. Alphabet. What is alphabet? Alphabet is nothing but set of symbols. Alphabet is a set of symbols. Generally alphabet is denoted with sigma. So sigma is, as per the definition, alphabet is set of symbols. So let us say I am taking symbols as A, B, then if you write in a set, this becomes my alphabet. So alphabet is set of symbols. It may be any combination of symbols. Generally it is finite symbols. So this is alphabet. So then the next one is, we call it as powers of alphabet. Powers of alphabet. So in the powers, so let us take the same example, sigma is equal to A, B is my alphabet. Then powers means first one is sigma power 1. Whatever alphabet is there, same as it is for sigma power 1. If you write sigma or sigma power 1, both are same. Then the next one is, so here the meaning is sigma power 1 is nothing but using that alphabet, strings of length 1 symbols. Strings of length 1 symbols is denoted with sigma power 1. So that's the reason here we call it as powers of alphabet. That's the reason here it is sigma power 1 it is. Then if you move on to the next one, sigma power 2, which means strings of length 2 over this alphabet A, B. So then if you take sigma power 2, you will get AA, AB, BA, BB. Since here the symbols are only 2 symbols are there, now also I need 2 length symbols. That's the reason you will get 2 power 2. So the 2 power 2, which means how many? 4. So you will get 4 in sigma power 2. If you move on like this, sigma power 3, then you will get, so that means sigma power 3 means what? Over that alphabet A, B, strings of, that means symbols of 3 length. So symbols of 3 length means what we will get? A, B, A, B. And similarly you will write BAA, you can write BAA, BAB, BBA and BBB. These are my 8 symbols. As I said, 3 length and 2 symbols are there. That's the reason you will get 2 power 3. And so on and so forth. If you continue like that, sigma power 4, you will get 16 strings in that particular one. So all these are powers. Now, in the powers of alphabet, there are 2 major things. Everyone should learn these 2 things. One is, we call it as positive closure. Positive closure. Generally, it is denoted with sigma power plus. Then the next one is clean closure, or one more name is there, we call it as star closure, which means sigma power star, sigma star. So what those 2 are? In the powers of alphabet, we should learn these 2. These 2 are the most important things. Sigma power plus, that means positive closure, and the next one is clean closure, sigma power, sigma star. So what is the difference between positive closure and clean closure? So let us observe here. Sigma power plus, that means positive closure is nothing but union of sigma power 1 union, sigma power 2 union, sigma power 3 union, and so on. You will get infinite. So that is what positive closure means. Then the next one is sigma star. So this is clean star. That means clean closure or star closure. Sigma star means, so before explaining this concept, we should know one thing, that is, if we have no symbols are there, how can we represent no symbols? No symbols represents empty string. No symbols means we call it as empty string. It is denoted with epsilon. So now in sigma star, you will get, in addition to this, that means you can say that epsilon, if you write in set epsilon, union sigma plus. So that means sigma star, the difference between sigma plus and sigma star is, in sigma plus, this empty string is not available. That's the reason we call that as a positive closure. But in sigma star, in addition to positive closure, whatever symbols are there in positive closure, all are included in sigma star. And in addition to that, you have one more called as empty string. So that's the reason I can say that sigma plus, that means my positive closure is always subset of sigma star. So positive closure is always subset of clean closure. So that's what powers of alphabet. So we discussed what is symbol, what is alphabet, and what is powers of alphabet. We all discussed all these 3. Then move on to the next one, language. So 4th one, I am removing all this. So now my next one is language. So what is meant by language? So what is meant by language? So before language, we should know what is the length of the string. So here W is a string. So if you want to define a string, we must have an alphabet. Let sigma is equal to a comma b is my alphabet. Then W means is a string which is obtained from this alphabet only. W is equal to, let us say, A, B, B. So this is my string. Now what is the length of the string? So length of the string is denoted with modulus of W. And how many symbols are there on that string, you need to count and then write the value. That is nothing but the length of the string. So here modulus of W, here W means A, B, B. So if you look at here, 1, 2, 3, 4, 5 symbols are there. That's the reason modulus of W is equal to 5. So this is what length of the string. Then we said already empty string is denoted with epsilon. So then move on to the next one, language. What is meant by language? Language is nothing but, this is my next definition, that means 4th one. So language, what is meant by language? If you want to define a language, first you must have an alphabet. Let sigma is my alphabet. Let sigma is equal to a comma b is my alphabet. Then I can define language. So language is a set of strings or an alphabet. Language is a set of strings or an alphabet. So let us take an example. Let sigma is equal to set of a comma b. Then my language L1 is equal to L1 means here I am writing L1 means set of all strings, set of all two length strings. Set of all two length strings or an alphabet sigma. That means what I will get in my language L1, you will get set of two length strings here. That means what? AA, AB, BA, BB. You will get these two. Now next, I am taking next example. L2 means set of strings started with A. One thing, maybe my writing is not that much neat. You listen my words carefully. So let L2 means what? Set of strings started with A. So what it means? So now if I write this language, L2 is equal to what? Strings started with A, right? So strings started with A means what? So definitely in my language, all the strings start with A. So that's the reason definitely A must be included in my language. Then AB, yes, it is there. Similarly, AA, yes, it is also. If I write BA, if you write BA here, that's a problem for us. The reason is, in the language, set of strings started with A only. So if I write BA, the string started with B. So that's the reason, don't include that. So then move on to the next one. You will get triple A and then AAB and so on so forth. You will get many more. So if you look at this language, in this language there are many strings available in this language. That's the reason I can say that this language is infinite, because many infinite strings are available in this language. That's the reason this language is called as infinite. Now move on to this. L1 consists of only finite set of strings. Therefore this language is called as finite. If you write many more examples related to language, like L3 end with A, or you may say it as substring of AB, all those things are examples to the languages. And then the next one is, after completing the language, now just I am starting my automata. What is automata? So why the need of automata came into existence? I think Alan Turing. So I think everybody knows that Alan Turing is a famous computer science scientist. So generally now also we will get Alan Turing Award, which is equivalent to Nobel Prize in the computer science field. So Alan Turing proposed initially. So actually why the need of this one is, the major thing is, just now we took an example, L2 is an infinite language. What is that? Strings started with A, which means A, AB, AA, triple A and so on. Now we have an infinite language. Is there any representation to represent my infinite language? Is there any representation which is in the form of finite only? Since it is a language infinite, so to represent infinite language, is there any representation in the finite manner? So the best answer is finite automata. So every infinite language you can represent, whether it is the language is finite or infinite, you can represent easily in the concept of finite manner. So that is the best one. We call it as finite automata. That's the reason this automata we call it as finite automata. So and then finite automata is categorized into two types. One is finite automata without output, and then the next one is finite automata with output. OP means output. So finite automata, I am classifying how many different types of finite automata are available. So now finite automata is classified into two categories. One is finite automata without output, and the next one is finite automata with output. Again, this finite automata without output is categorized into three types. One is D of A, and the next one is N of A, and then it is epsilon N of A. D of A means deterministic finite automata. So we will discuss in detail what is this deterministic finite automata, and then similarly non-deterministic finite. N of A stands stands for non-deterministic finite automata, and this is epsilon NFA. We call this as epsilon NFA. We will discuss all those things in coming sessions. Don't worry about that. Okay. So now this is again, this finite automata with output is categorized into two types. One we call it as Murray machine, and one more is Mealy machine. Murray machine and Mealy machine. So this is the entire categorization of finite automata. And this finite automata, it is classified into two types: finite automata without output and finite automata with output. And this finite automata without output is again categorized into three types: DFA, NFA and epsilon NFA. And here finite automata with output, it is categorized into two types: Murray machine and Mealy machine. So now in this finite automata without output, so just I am giving a example of finite automata. Everybody knows about electric switch. So I am just giving finite automata example. So now everybody knows about electric switch. In electric switch, you are having two states. One, generally it is always in the off state only. So that is the starting state. And then you are having one more state called as on state. Now, so what symbols are there? That means when we are in the off state, if you want to move to off state to on state, you need to apply push operation. You may say it as that button, that switch, you need to push it. Then that state off is moving to on state. Similarly, and when we are in the on state, if you push one more time, then you are moving from on state to off state. Again here also push. This is a simple example of a finite automata. So here all this, don't worry about this notation. We will discuss in detail in the coming sessions. So here all this circle one we call it as states, and this arrow symbols we call it as transitions. All these you people know about direct graphs. So here we are having a transition from push button. So from this state to this state, and similarly this state to this state also. Off to on to off, both are there. And here these represent states, and these are my transitions. Okay. So this is the best example of a finite automata. Now let us move to the definition of DFA. So today we will discuss what is DFA, and then we will end today's session. Okay. So DFA, what is meant by DFA? So here I am giving an example of DFA. Deterministic finite automata is a phi tuple. So what those phi tuples are? Q, sigma, delta, Q naught, F. So we need to know each and every tuple, every value in this tuple. So here this is a phi tuple. So DFA is a phi tuple. Where what is Q? Q means set of states. Q means what? Set of states. Sigma means input alphabet. What it is? Input alphabet. Delta is a transition function. So and here we need to know the transition function, where how it is mapping. Delta is a mapping from Q cross sigma to Q. Q cross sigma to Q. And then Q naught is the initial state, or you may call it as starting state also. Q naught is the initial state or starting state. And F is the set of all final states. So now in this, in all these three definitions, DFA, NFA and epsilon NFA, all those definitions are phi tuples only. But the only difference is all the definitions, this Q is there, the sigma is there, this Q naught is there, F is there, delta is there, all are same. But the only change between DFA and NFA and epsilon NFA is this transition function. Based on the transition function, whether it is DFA or NFA or epsilon NFA, we can identify. So I will give an example of a DFA. DFA can be represented in two ways. One is transition table and other one is transition diagram. Which one we are looking here? So that is an example of a transition diagram. So similarly, you can find out one more representation called as transition table. We will look into those two concepts in the next session. Thank you so much.